Good afternoon. And we are going to have Damian Maingi giving a talk. He is from University of Nairobi, Kenya. And the title of the talk is Vector Bundles Construction via Monads on Multiprojective Spaces. Please, my friend, you can start.
All right, thank you very much, Merav. Actually, it happens to be here. I'm in Nairobi, and Nairobi is the exact same time as there in Kyiv, I think, right? Yes. So yeah, so my talk is entitled Vector Bundle Construction. Yeah, fine. I mean, you've already been told. I'm Damian, based in Nairobi, and I start by thanking the organizers for the conference. I just got an email some time back, and then I thought, okay, why not? And then I've actually been debating on what exactly I'll talk about. So I hope in the presentation, I have not mixed a few of my results and things, but it's okay, no problem. Yeah, so about vector bundle construction by monads or multiprojective spaces. So I'm going to I mean, this is the outline of my presentation. So I will have an introduction, and then give some motivation of the research, and then some background, and then I mean the whole connection between now the monads and the associated vector bundles that arise from that. Okay, that's going to be my the outline of my talk. And so straight away we go to the introduction. So in this presentation, I hope this will not, let me carry this, can I take it away? Yes. Ooh, I'm opening many other things here. And to take it away down here. I hope it will not interfere. Can I hide it somewhere? Or maybe up there? I don't know. There. Okay, fine. Yeah, so in this presentation, I aim to construct monads on multiprojective spaces and study their vector bundles. We shall, well, so forgive my exchange of I and we, mixing the pronouns, but anyway, that's English. So we shall denote by X the space over which we construct our monad. I would say mostly what I did is just to generalize results from projective spaces. And so instead of using P to some dimension, I just use X, okay, for that. And then, so we'll use X. And then the cohomology bundle, really, basically, that's associated to the monad, we'll use E to represent that. And then, so my main result really for this talk is just to talk about my X to be this Cartesian product. I mean, this multiprojective space P, A1 all the way up to PAN. And then this is more like a corollary, which is motivated by some previous work, okay, that's done elsewhere. Yeah. And then just some statement I make here, probably this statement may be relevant for this talk, I don't know, but I could say that I will not distinguish between a vector bundle E on X and its locally free shift of sections. Why? Because I would say, like previously, anyway, when I've gone through the talks of the conference, I think there's some kind of bias towards differential geometry as opposed to algebraic geometry. But anyway, since I'm from the algebraic geometry side, I'm mostly dealing with locally free shifts. And so anyway, I mean, just the connection is this, that there's that equivalence of categories between the category of vector bundles of rank R over X and the category of locally free shifts of rank R on X. So really, I mean, the bundles we are talking about that are associated to the monads we have are actually, we're just dealing with the locally free shifts. And really, if you think about my monad, and when you look at it, you'll just see that it's actually like a complex of line bundles or direct sums of line bundles. Okay. So the motivation behind my study, hopefully you can hear me, by the way. Can you? Because I tend to, where I live, there's a bit of noise and things happening, but hopefully they don't.
Yes, of course. Of course. Very,
Okay,
very
thank you very much.
clear. You sound very clear
All right.
to me.
Okay.
Very clear.
Thank you very much. Okay. So the motivation for my study is, well, first to observe that the difficulty in constructing non-splitting or in decomposable vector bundles on algebraic varieties increases when the difference between the rank of the bundle and the dimension of the variety increases. So indeed, the most important or interesting problem is to find or construct indecomposable vector bundles low or small rank in comparison with the dimension of the ambient space. And this really is actually motivated by what we call the Harshon's conjecture. And basically what the Harshon conjecture just talks about is on projective varieties, any vector bundle splits, okay, of low rank or of small rank. In this case, we're thinking of dimension 2, dimension. Well, I mean, now if we talk about the projective space, dimension less than or equal, less than 7, less than 7. So here I just mentioned the context. We have the famous Harshon's conjecture concerning the existence of decomposable rank 2 vector bundles. Here we can just say low rank, I mean, to think of dimension, even rank even 4 on n-dimensional projective spaces n greater than or equal to 7. A lot of work has been done, and there have been some bundles. I mean, the most famous one is the Horrocks for bundle, which is rank 2 vector indecomposable, okay, rank 2 vector bundle on P4, right? And a few others have been done. So I'm saying this is my motivation, because in the process of generalizing the space, then perhaps, or when you relax the space, you could with some kind of polarization, you could play around with the dimensions and actually get some small low rank vector bundle, right? So the background now for our study, monads, okay? So mostly monads appear in the context of or within algebraic geometry. They are useful in the construction of vector bundles. And maybe here it would be nice perhaps for me to mention that with regard to projective varieties, there would be like 3 ways that you can construct vector bundles. One of those would be, I think, using the Serre's construction, okay, or correspondence. Or you could use, okay, 1, 2, you could use Murayama's elementary transformation of vector bundles. And then number 3, which is what I focus on for my talk, is now on monads, all right? They were first introduced by Horrocks, who showed that all the vector bundles E on P3 is just dimension 3 projective space, could be obtained as the cohomology bundle of a monad of the kind this, and like I mentioned earlier on, you can see these are direct sums of line bundles, okay, on P3, right, with the given where A and B are, these maps are actually matrices whose entities are homogeneous polynomials of those degrees. Well, yeah, so that more or less covers my motivation, my background, and, things. So now we can get into business, which is now the monads themselves. So definition. So what's a monad really? Actually, and this more or less, there's the monad from the categorical aspect of definition. So the monad I'm talking about here is we are given some smooth projective variety X. So a monad on X would be a complex of vector bundles of this form, which is exact at A and at C. And what we were now saying that the arising bundles, basically what we call the cohomology of the bundle, would be given by the kernel of this map, quotient by the image of this other map, which I'm calling E. So E is kernel of beta and the quotient by the image of alpha, right? In this monad, and then something that is useful, and perhaps these are the arising things which you could say from the past or more previous work has been done on when you studied out the arising bundles from this. So we have what we call a display diagram, okay? So the display of this diagram will just basically mean a diagram of, I can call them columns and rows of short exact sequences that are derived from the monad. So meaning what? That we do have our monad, this is our monad really. And so the co-kernel of this map alpha would be Q, which is a bundle. And then we have the kernel of this map beta would be K. And now E is what we are calling our cohomology of our monad. And this is now like what we end up like focusing on in the second part of the presentation, all right? And then here I just have from here all of this. Then we have Q is a co-kernel of beta. I don't know what else we say here. So we say that, and then E is a cohomology of the monad. And then you can say the rank of E would be actually, rank of E would be rank of B minus rank of A minus rank of C. And then you'd have what you call a Chang polynomial. of E would be given by this. And numbers, you would have the first Chern class of E would be the first Chern class of B minus first Chern class of A minus first Chern class of C, thanks to our display diagram. All right, next we have well, more definitions, more this like now generalizing a little bit more, but like towards our goal, which would be a linear monad, all right? So given X is again, so maybe missing smooth, I just say non-singular projective variety. Have L, my very ample invertible sheaf, and some K vector spaces, UVW, a linear monad on X would be a complex of this form, which is exact at this and at here, okay? And now, in other words, saying alpha belongs to this, and beta belongs there. And then we can say actually again, the next definition, which I don't know that can be seen, but it's just saying that we have a similar thing about the cohomology bundle arising from this. So a torsion-free sheaf E on X is said to be a linear sheaf associated to the linear monad if it can be represented as the cohomology sheaf of the linear monad, all right? So here, let me just remove this for the sake of seeing that, but anyway. Yeah, so E is this, the kernel of beta, quotiented by the image of alpha, and the rank we already mentioned, and the dimensions also are given there. Okay, hopefully this will not disturb us again. Or maybe I put it up there. Let me put it somewhere up here. I hide it there. Okay. Yeah, so I think we need to see the menu above. Okay, so more definitions still, more definitions. Where are we going now? Yeah, so now the existence of monads on projective spaces, I would say the first like main important result, which other things have been built on or other works that we've done, is thanks to Gunnar Fløystad way back in 2000 in communication algebra. So this is the result that he came up with. Okay, here I call it a lemma that says what? Let K be, some integer, positive integer. There exists a monad on PK, the dimension projective space, whose maps are matrices of linear forms. This monad exists even only if at least one of the following is satisfied. What? That B is greater than twice C plus 1 less the dimension of PK. Actually, here, anyway, I made a mistake here in my presentation, but just to say that this and should be on this side. Okay, this condition and this condition is 1 or the other one. So at least one of these two are satisfied. So this I should put or here, okay? And this establishes monads on projective spaces. And now my previous results, well, I'm not yet at where we are supposed to go today in our results, but just to say that the next thing is just to say, in the next, well, much later on, 2014, I generalized the space. Now I study monads on, well, okay, here is worthwhile mentioning that Marchesi and 3 other people have actually generalized this over more general projective varieties, okay? The existence of monads on projective spaces, okay? But not Cartesian product or multiprojective spaces. Eh? So here now I have my result, or one of my results on monads. Okay, these are monads. So let X be this multiprojective space of Pn, projective space dimension n, cross with projective space dimension m, and we take L to be an ample line bundle. And ample means rho and sigma r greater than 0, much less than 0. And then we denote n by the dimension of this -1. So let alpha, beta, and gamma be positive integers such that at least one of the following conditions holds. So the conditions are similar to the Fløystad conditions. In fact, is more like derived from that. So from now on in my talk, when I say Fløystad conditions, I'll mean these conditions, okay? Where I'm talking about either this or this is satisfied. What? Okay. And this result was for if and only if. So in my case here, I mean, that result I had was for one way to say that this monad exists, provided we'd have one of these results, one of these conditions holding for this. Again, here, this I'm just mentioning, I'm not proving anything for this one, because I'm just like now just extending or generalizing monads for a more general, let's say, projective space, okay? I mean, in this case, a multiprojective space. And the twist is some integers, all right? So something else that recently I did was to look at a different kind of monad, but it's still a monad within. That says what? Let n, m, and k be positive integers. Then there exists a linear monad on X. In this case, now my X is, you can think of it as two copies of Pn cross two copies of Pm. So this monad exists where, I mean, the middle part is just direct sums of, these are direct sums, okay? And anyway, the way I prove, okay, well, again, the proof for partially, the proof for the proof that Floystar gave, again, just to mention, was partially one way of proving this is an if and only if theorem. One way was to construct actually these maps, you know, and remember the maps for the monad, in case we're dealing with here, actually are matrices, all right? So actually you're able to construct the matrices, you actually establish the existence of the monad. So in my case here now, in this recent result was to actually construct these maps, and having constructed these maps, actually establishing the existence of this monad, all right? Again, this is some result I'm just mentioning or posting it there, but not really, more like just to give you motivation or to appetize you for the talk, okay? So we're still, you know, how do I say, motivating ourselves, okay, of building up towards the important thing. And then one more recent, like a more generalized version is like now a more generalized space. I mean, like now I have you know, let A1 up to AN and K be positive integers. Then there exists a linear monad on X. Now my X is this space. I think of PA, two copies of PA1, two copies of PA2, all the way up to copies of PAN. So we do have this monad. And actually, again, what I did for this case, here I'm just giving you snippets. I'm not giving you what happened in those papers and things, just to mention what concerns monads, okay? My talk is actually based only on two things. One, monads, and then the arising or the associated vector bundles. So this is more like the first session of my talk, okay? And so, again, so like I'll say that if we find a nice way of building or constructing these maps, I mean, these matrices, then actually we establish that this monad does exist. And then we can go to the next part, which will be now studying the associated cohomology of these bundles, okay? I mean, cohomology of these monads, sorry. So the first, now I can say maybe I go to the first proper result of the, here when I say goal, is more like now my presentation here, which is not published anyway, just in the archives, okay? This is now the first result that I present and give you some proof or sketch some proof, okay? What does it say? That, you know, let X be, now my projective space, like when I began the talk, I mentioned that my X is my ambient space, and I will just talk about PA1 cross all the way up to PAN. This is my multiprojective space. And now my ample line bundle is this one, OX, alpha 1 all the way up to, or twisted by that. I mean, ample means alpha 1 all the way up to TR greater than 0. And then I denote by N this dimension less 1. Then there exists a linear monad on X of the form. This is the form of my monad. Here, again, hopefully I don't confuse the notation. So this monad exists if at least one of the following is satisfied. One, or A, beta is greater than or equal to rho plus 1 less the dimension, this n of ours, and beta is greater than or equal to alpha plus rho, or the other condition is just beta is greater than or equal to alpha plus gamma plus n. And so here is give you a quick sketch of the proof for this. So for our ample line bundle, this is our ample line bundle. We can define a seg embedding this one X from my X to this space, which is a projective space. And remember my N, now my dimension of, actually the dimension of this space is just where N is A1 plus alpha 1, choose alpha 1 times A2 plus alpha 2, choose alpha 2, all the way up to AN plus alpha T, choose alpha t minus 1. This is the dimension of my projective space. And then now if we suppose that one of the conditions of flow starts are satisfied, now I picked that if we satisfy one, then we can actually take the other one also. So the flow start conditions, remember, so if one of the flow start conditions is satisfied, then we would have a linear monad. Actually, since by flow start, we've actually established existence of monads on Pn, a projective space Pn. So we do have this linear monad existing on my Pn. And it so happens that in our case, we actually have our specific Pn, you know.
Yes, so here's the
Sorry, I can't hear you. There's some interference. The question, okay, I don't know if I get your question, but these A1s are different from alpha ones. Is that what you're asking? I hear you, but there's some like scratching, so I don't get what you're
me
saying.
as well, Sergey. It's very hard to understand because you sound like very blur on your microphone.
Yes.
So I'm sorry, I didn't get your question as well. So I don't, maybe if you can write or something or.
Okay.
Yeah, maybe you write.
Now it's better.
Damian, I can hear you very, very clearly, but Sergey, it's very hard for me to.
Sorry. And now it is better. Not.
Okay, just try. Okay, try again. Just try again.
The question is, can you hear me? Yes, you hear now.
Maybe better. Yes, maybe better.
Yes.
And now, okay. So, how do you make this correspondence? So, if you have alpha one and A1, alpha one, A2, alpha two, but here N and T. So, this is different indices or not? No. Okay. So, sorry.
Okay, I get your question. I get your question, though I don't hear the message very well. Yeah, I see what you're talking about. I see what you mean. Yeah, I see what you mean. They should be the same indices. Yeah, you're right. If I'm using yeah, this should have been N, okay?
Okay.
I get your question actually. Yes. So you can have alpha 1 all the way up to, this corresponds. The alpha A1 up to AN. Then you have the twist, so it's alpha 1 all the way up to alpha N. Okay, thank you. I get it. Okay, I should note that somewhere. Okay. Thank you. All right. So then we have said more questions. Any more questions, by the way, just in case? Okay, we continue. Okay, good. Yeah, so then we've said that thanks to flow start, if we suppose one of the conditions hold, then we do have this monad. And on Pn, whose morphism are matrices A and B, whose empties are monomials of degree 1. And once we have the monad now on our Pn, then this monad actually we can just conclude it will induce the the matrices. These are the matrices we have, and the matrices A and B are entries, basically morphism from here to here, and then morphs from here to here. And now thus our A and B will induce a monad on X. So this is the monad they'll induce. And this is the monad we require actually, whose morphisms are. Now in this case, the monad where is the monad? So we have this monad with these morphisms. And now the new monad that we induce is actually this one. These action maps should not be, I think they normally are above, not below. Anyway, so this is now the new monad. And so we can say that's a first result that we wanted, which is existence. The first thing for us to be able to move forward is, at least we need to know or to guarantee that actually these monads do exist. So that's number one result. And now once we have that, then we can, before I go to now the second aspect of talking about the arising or the associated cohomology of the monad, now this again, I said earlier on when I began, it's like I was confusing some result. Well, not confusing, but confused about what to talk about in this talk. But basically, is now I just took the second, I can call this more like a corollary. If I fix now, remember our monad was A1, my space is A1 or N. So if I just fix them to be A1 equals all the way up to AN, and there are 2N plus 1. And then I choose my alpha 1 to alpha N to be 1, then I have this monad. Why I said the motivation for this is more like a study on vector bundles, especially on what are they called? Instanton bundles. Anyway, that was just something I just threw in there. Now, the second thing I want to say before I leave monads is just to say that I thought it would be nice to see how some of these maps look like, you know, these maps we're talking about. So I took some kind of example, which I can call like a construction. I call it explicit monad construction via matrices. So earlier on, we said that one way you can actually, I mean, if you can construct the maps, then actually you can establish the existence of the monad, or you can prove the way we've just proven, right? So now if I choose or I relax my space to be, P1, let's just say how many copies? M copies of P1, P1 cross P1 cross P1. And I would say this would actually inject into some Pn. I mean, I can just say where n equals to twice n plus 1. So let this be the seg embedding, which we can define as follows. So I defined, so these are the coordinates for my first P1, coordinates for my second P1, all the way up to the coordinates for my, I'm saying m copies of P1, so the mth copy of P1, all right? And then this injects into, well, now this is into 2n plus 1. And then here, if you want more specific relations, you can actually do the computation. So first note, we are taking m copies of P1, then we have n is just 2 to the m minus 1, the computation, and then you just compute something you end up with. N equals, this equals 2n plus 1. So my n is actually 2 to the m minus 1 minus 1, all right? Now, what is it we want to see here? From, again, we can just say from the Floystad, we do have, this is more actually a corollary of the Floystad monad, in the sense that, what he was using as PK in our case here is OP2N, 2n plus 1. And then the twists were just minus 1, minus 1. And then I don't need to check the conditions. I just want to construct the maps, all right? So from this, we can induce a monad on this multiprojective space, and we will induce a monad from there. So what I did here is just to have some kind of relation between, so by giving the morphisms, now morphisms A and B, I want to construct those that satisfy two conditions. One, that the B times A is 0, and A and B, okay, I should say bar A and bar B are of maximum rank. Of course, this is true because these are projective space and they are not all zeros, they never be. So they will always be of maximum rank. So what do we do? Well, see, I just have a statement here, which I don't know whether we need to read or we can just skip. So from A and B, whose entries are x0, xn, y0 up to yn, the homogeneous coordinates on Pn, P2n plus 1, we give the correspondence for the seg embedding using the following table. So I do have a table here. Now, let me just show you two tables. So one table here is, so we have the homogeneous coordinates on P2n plus 1, which are the x0 all the way up to xn, y0 up to yn. And you see via the seg embedding that we've just defined above, this one here, we actually have some association. Now here I'm just using some kind of counting. If you want me to think of it as a counting system. So where now x0 is represented by A000 all the way like that. x1, A00 all the way like that. Now, remember, well, so these are the coordinates for 2n plus 1. So I want to see how they look like when they're represented as, you can think of them as monomials, right? I mean, you are just multiplying the coordinates of this and this and this and this, all those P1s. So I had this short form representation, and then I have the long form for each one of them. So what I'm calling AX0, which is A000 all the way 0, is actually if I multiply all of them as zeros, okay? The coordinates are hard. My coordinates here are this one. So I have alpha 1, 0, alpha 2, 0, all the way up to alpha M0, all of them. So we have alpha 1, 0, alpha 2, 0, alpha 3, 0, alpha 4, 0, all the way up to all of them are zeros. If we pick now X1, will just be, well, X1 is A00 all the way up like that. So we have all of them are zeros except the last one, which is 1. If you shift now, you have all of them are zeros except this one. Then here you just have zeros except here. And so on like that. So this gives us some kind of correspondence. And so if we do have the matrices, so my aim was just to have, if I have these matrices A and B, which are in these coordinates, then actually I can induce a monad which are in these coordinates, coordinates of those products. So I end up with 2 matrices, which are this. Anyway, I've more or less hurried up there, but anyway. So specifically, we define 2 matrices by A and by B as follows. So my B will be this matrix, and my A is this matrix. Now, I don't know, sorry, the matrix, I didn't work on fitting it here, but anyway, just to say that B multiplied by A would actually end up degenerating, would end up being 0. And we've said that A and B are, well, these are coordinates in projective space, so they will never be 0, all of them, so they are maximal rank. So that now brings us or establishes us to, yeah, I've already mentioned this. So that's that. Is that finished? Let me see whether that ends. Yeah, so that's it. So ladies and gentlemen, that's the first part of my talk. I hope I've not taken forever because now I need to mention something about the vector bundles that arise from these spaces. But let me just say something small here before I go away from monads. That, okay, I have spent time on this, but part of the reason is because there's something I'm working on, which I don't know if I'll finish. I didn't want to talk about results that are not yet conclusive, which may come out as part of the proceeding for the paper for this conference. I don't know. But basically, the idea is this. Let me just illustrate for you the idea, which I found exciting. And then later on, the vector bundles, hopefully. Shortly, just forgive me for this one. This one. When I submitted this paper for review, actually the editor, one of the comments they made was, I mean, is it possible to, when you generalize the maps, you can actually talk about, like the twists here. Now, they just maybe, the way I have alpha 1 or minus alpha 1 all the way up to minus alpha n, by just playing around with the maps for a projective space. So that's something I was playing around with, and I found is actually not very complicated to write up. And so it's actually following this kind of thing of playing around with these matrices that I've just illustrated here. That's why I say that I spend some time on this kind of. It makes it's mostly to motivate me. So now allow me to give you a brief talk about the vector bundles. So the second part of the talk, which I should finish very briefly. I believe I have a few, like maybe 5-10 minutes or so. Not 10 minutes, maybe 5-6 minutes or so.
Yeah, 6 minutes, Damian, 6 minutes.
Okay.
Yeah.
Okay, so from our monad, now we can look at the cohomology bundle that arises from it. So I just give you some quick background. So suppose, remember our ambient space, our multiprojective space is PA1 cross all the way up to PAN. And so the Picard group of this is actually, Zn, all right? And so we can actually talk about, we can let G1, G1, G2, Gn be generators of this Picard group of X, all right? So we can denote by this, OX, G1 of the generators. Now these are the pullbacks. Each one of them, P1, OP1, all the way to all of them tensored by PN, OPN, GN, where each of these P1s are natural projections. You're projecting this space onto each of the PAI. I mean, PA1, P1, you project this to PA1, project the whole of X, and so on like that, okay? So for every line bundle on X, a vector bundle E, we will write E twisted by G1 up to Gn as this. E tensored by OX twisted by that. And we'll write this representing its corresponding divisor. And then the normalization on X with respect to our ample line bundle X will be defined as follows. So we said D to the degree of our line bundle, since the degree of E twisted by minus KE, now this minus K is some integer that exists, so equals En. Now there's some mistake here, but anyway, the dimension of, so this is A1 up to AN, so N, K, now what is my K here? The K is supposed to be this KE. And then this is times what? This is supposed to be rank of the bundle, actually. So here is some notational problem anyway, yeah. So there's a unique integer KE such that 1 minus D, again, this is D times the rank of the vector bundle, is less or equal to the degree of E over L, and is less than 0. And then we say that the twisted bundle, EL normalized, okay, is called the normalization of L normalization of E. And the motivation for this, or the reason for this actually, is for the associated bundles. I mean, the way we're going to prove, again, earlier on we mentioned that when we started the talk, we wanted to look at, is it possible, given some monad, once it exists, to study the bundles that are associated to the monad, and really studying them just to check whether they are simple. Simplicity means they're decomposable. And for that, we need stability. And for stability, we need this normalization. That's basically why I'm doing all this, okay? Hopefully it's not taking forever. So let me just mention this briefly. I'm running out of time. So once we establish that, then we have what we call the Hope criterion of stability, which just says that for a polycyclic variety X with Picard number N, let L be an ample line bundle and E be rank R greater than 1 or vector bundle over X. So if this homology group X over this normalized twisted by P1 up to Pn is 0 for Q lying between 1 and the rank less 1, and every P1 belongs to Zn such that the degree is less or equal to 0. Then we say E is stable, is L stable. And so this criteria, so I'll just mention very quickly so I don't run out of time. This criteria now, let me just show you the vector bundle. So here I will just give you the 2 slides about the bundles. But anyway, so from our monad, actually that we had, it was just OX minus alpha 1 dot 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 minus alpha, well, T, like some alpha, then to this map to this one and to this one. So the kernel of that monad, actually the kernel bundle is actually F. So let F be a vector bundle on my space defined by this short exact sequence. So then F is F stable. And the stability, okay, with this polarization, we'll just use this kind of criteria to prove. I mean, that's what we used. Again, I'm not going to talk about it. I've run out of time. But basically, the idea is to make use of the Hope criterion of stability, which is that to end up proving that this vanishes, okay? For P1, I mean, the sum of P1 all greater than 0 and Q lying between 1 and the rank of, again, this is supposed to be rank. Here I made, again, notational mistake. Rank of F minus 1, okay? So that's one thing. And then now with that fact, we can now prove the last thing, which is that now the cohomology bundle of our monad that we have established, E, is actually simple, all right? And so the simplicity for this, I proved. Okay, most of these details are in archive. Okay, the paper is in archive anyway. But so the details for, I mean, the way we prove simplicity of E is to rely on the stability of F, all right? And then, just twisting and taking cohomology, and, then we just do some comparison, and then we end up with our simple vector bundle E. And so if it's simple, then it's indecomposable. Then again, I mean, my space is big, and, so just playing around with numbers, you can get something concrete. Anyway, so that's that. Then I mentioned some of the references that are very important is this paper of Ancona Ottaviani. I mean, on stability and establishing this Hope criterion of stability. And then later on, this more generalized in another paper. But then I talked about Gunnar Frostad's paper, which is very important. And then the others over there. I stop there. I ran out of time, and I think this is enough. Thank you very much for giving me this opportunity.
Thank you, Damian, very much for interesting talk. You're very motivated. Wow, amazing.